Hello, and welcome back again to Astronomy 305. At this stage, I like to say this is the last lecture notes of the semester. I would like to congratulate you on surviving through the previous lecture notes that are, basically voiceovers of the slides. I know they must be dreadfully boring. I would imagine that live lecture is much more interesting. At least I hope it is, because I just think that this must have been you know, like I said, dreadfully boring. And so um, let's just move on through this last lecture, and we can congratulate ourselves for making it through this class during this extremely uncertain and unique time in our lives. And hopefully we won't be repeating this anytime in our future. So we're going to be talking about the habitability outside the solar system. We talked about habitability in module 10, and we talked about the Drake equation in module, I don't know, I called it D1 just because it was an insert, if you will. And today we're going to talk about some of the information that has led us to understand the terms in the Drake equation, which are F sub p and N sub e. Particularly N sub e is the one that we're really trying to work on right now. So this particular lecture is going to be concentrating on astronomical information that will help us hone down and understand how it is that we can measure N sub e and what we mathematically might try to predict what it might be. So we were going to think about habitability in terms of life basically on planets and moons, and planets and moons around stars. As we've learned with our own star, it ages, and as it ages, it changes, and eventually it will evolve to the point, or age to the point, where the solar system will basically not exist anymore, and in its place will be something we call a planetary nebula, if you remember that. So turns out that not all stars will die in this way. And so what we have to do is think about the star cycles and their star lifetimes, and account for all the different various types of stars there are out there. So what we're going to do is we're going to talk about the various types of stars, and then we're going to talk about how that is related to habitable planets around them. Okay, so to learn about stars, first we'll learn about how we categorize them. I'll give you a brief history lesson on that, and then we'll talk about which stars would make good suns. And that's kind of a funny question, because basically which stars would be good for finding habitable planets around is more like what we're interested in. Then we'll briefly talk about how we find planets around other stars. I won't spend a whole lot of time on that, but then I'll talk about what we have learned from extrasolar planets and what we know about them. And then I'll talk about how could we detect life on an extrasolar planet. And that would be very indirect. Right now, to be honest with you, we are able to determine if a planet is in a habitable zone around a star. That doesn't mean that we've determined it's habitable, however. So now what we're doing is we're just at the very beginnings, the inception of stretching current technology to try and understand whether some of these planets are actually habitable, never mind whether they have life on them. So then the next question is, can we determine whether they have life on them? And so we'll end the lecture talking about that. Okay, and then we're going to end up talking a little bit about the most common types of planets that are around other stars. And I think the two videos that we saw with the Drake equation discuss the rare Earth hypothesis. So we won't be talking about that in very much detail, but you can review that if you wish by watching one of those space-time videos. Okay. So we're not going to get into how the Hertzsprung-Russell diagram developed, and you might be thinking the Hertzsprung-Russell what? We did show this diagram. For short, we call it the HR diagram in Chapter 10 or Module 10 when we talked about the evolution of the sun, and remind you that it's a diagram of the temperature of the star, surface temperature of the star, versus its luminosity or its energy output in the form of light, its power output in the form of light. So it turns out we can learn a lot from that diagram, and we're not going to go into a lot of details, but of course I will be showing that diagram again in this particular module. Well, I've shown this diagram before, and I think this is the third time you've seen it during this class. And of course, the reason I'm doing that is because this slide is your one-stop, get everything you need about this course, okay? And so I'd like to review this slide one more time. And it's really, I think, key for you to have a good feeling for the story on this slide because it puts everything together. Now, our story starts in the upper left-hand diagram with the boxes that are expanding, okay? And this is a depiction, if you will, of our expanding universe through time, where things were hotter, and there's the small box you can see, hotter and denser and everything closer together. So as the universe expands, all the things get further apart from each other until we get to the modern day. So the universe is expanding. The universe is very old. It started in a Big Bang about 13.6 billion years ago. Hydrogen and helium were forged within the first 3 minutes. And then atoms some 400,000 years later. I'm not asking you to know all those details, just listen to the story. And then a long period of time went by while matter was gravitationally collapsing. And eventually, the gravitational collapse of this matter on the scales, some of it on the scales of galaxies, formed what are modern day galaxies. And within those galaxies formed stars, and the gas collected around its own gravitational self-attraction, and then would collapse down to form the stars and the planets. And so this was occurring in billions of small locations isolated around inside these galaxies. There's gas that still exists in these galaxies that turns into stars and planets. Then the stars age. When they die, they will explode or expand into planetary nebulae or explode as supernovae explosions and blast the gas back out into the regions between the stars from which new stars will form. And during that period of time, the chemical elements, carbon, nitrogen, oxygen, the rest of the periodic table are forged in the cores of these stars through nuclear fusion being what generates the power which makes the stars shine. So in our upper right-hand corner, we have a typical galaxy that we might see in the universe. And I'm just reminding you that there's 100 billion of these or so spread out throughout the universe. And if you remember from our previous lectures, they tend to string together along filaments and then cluster into big clusters. And we live in the outskirts of one of these clusters called the Virgo cluster, about 65 million light years away from the center of that cluster. And our little galaxy is only 100,000 light years across, so it's tiny compared to that distance, a pinpoint. And so these 100 billion stars come and go and live out their lives in this cycle, which we call formation, and then we'll call it main sequence. That's the middle-aged lifetime period of a star when it's healthy, doing its nuclear fusion, has planets orbiting around it, much like what the sun is doing. And then, of course, the stellar death. And then you could draw an arrow looping back up to formation because the gas from which that it spewed out there in the universe, or I should say, in between the stars of our galaxy again, um, allow it to um, allow that gas then to condense into new stars and systems. So in the orange box is to the lower right is basically that entire cycle that I've been talking about. The upper picture along that circle of life, if you will, for a star is the formation process. You can see the planetary disk forming around it. And then later, the planetary disk clears out, and you get planets and maybe an Earth like planet, like with the moon, that we're showing here in this diagram as we go clockwise around this cycle. And then, of course, later the sun will die or explode, and we have something like the picture in the 8 o'clock position, which is an exploding star. This is actually a supernova, and it's expanding at tens of thousands of kilometers per second. And you can see that it's been enriched with all the chemical elements that were forged in the core of the star, and also from previous generations of stars from which that star itself formed. And then again, it goes through the cycle. It doesn't fall back in on itself and contract, but that gas spreads out, gets incorporated with other gas clouds, and those gas clouds then form new stars. And you get multiple generations of stars going on and on like this. And we think our sun is this second or third generation star in our galaxy. So in our neighborhood of the galaxy, we are sort of the great grandchildren of the original solar systems and stars that existed here, starting some 10 billion years ago. Now, let's look at the picture of the Earth and the Moon there. That's in the 4 o'clock position. What we're going to do now is think about what might happen on a planet like that. That's going to move us to the lower left part of the diagram and bring us to the end of our little story, which is you could have life start to form. And we've talked about that in great detail in this class, how that might happen. And we've talked about the 3 requirements for life: the energy for life, the chemical elements for life, mostly the hydrogen, the carbon, the nitrogen, the oxygen, and turns out phosphorus for phosphate molecules. And so then life might form, and life might form to the point where intelligence forms, or evolves, I should say. And from intelligence, you may evolve into a technological civilization, or at least one that is intelligent enough to look back up at the stars and start asking questions about the universe, and maybe even develop a methodology to have a dialogue with the universe, which is what I would call science. Science is basically our language of having a dialogue with the universe to try and understand what the universe is like. And we have to use experimentation to sort of tickle information out of the universe slowly over the years. But this life basically formed from the process of the universe itself. I mean, it really is as much a part of the universe as a planet is or a star is. So you and I and our brains are as much a part of this universe as a planet or a star or anything else that has formed out of the physical processes that have governed the evolution of the universe. And so, in a sense, we are the universe itself. You can't argue that. And yet, we look back out at the universe itself and ask, what is this thing? And one might even go so far as to say that we are the vehicle through which the universe itself is developing self-awareness and asking itself, what is it? And that's kind of an interesting end to this story of this slide. But as I said, this is the story that is the nutshell that puts humanity in perspective, a cosmic perspective. It puts life in a cosmic perspective. It puts astrobiology in the cosmic perspective. And that literally is what this class is about. So this slide really is your walk away. If you were to need to tell somebody in a 5 minutes elevator pitch, what did you learn in Life in the Universe when you took it, or what is the story of life in the universe, then that's the story, the one I just went through. Our journey to learn about the different stars that exist in the galaxy and in the universe started about 100 years ago. And it started with a group of people at Harvard University. I show you a picture on the right, and this is a picture of William Pickering. He's the only man in the photograph. And he collected all of the female PhDs in astronomy on the planet, which you're seeing here in this photograph, and collected them to come work at Harvard to basically become his computers. And he did this because A, they were intelligent and very smart. B, they were highly educated. C, he didn't have to pay them hardly anything. And D, they had no rights as PhD astronomers to use the telescope or anything like that, so they couldn't be in competition with him for telescope time and things like this. However, he revolutionized astronomy by hiring them in ways he did not anticipate. Several of them were deserved to have Nobel Prizes for their work, which they never did. One of them discovered that hydrogen was the main element that was in the stars. One of them classified all of the stars, and another one determined a method to measure the distances to very, very distant stars, and that revolutionized our understanding of cosmology and how big the universe is. So that really led to modern astrophysics and astronomy as we know it. So they were very instrumental people. One of the most famous is Annie Jump Cannon. And if you look at the picture of William Pickering, she's two to the right of him and wearing the gray dress. She was very famous for basically helping us understand what we call the spectral sequence of stars. And I'm going to explain that to you now. What I'm showing you in the left panel is a blurry image of some stars in the sky. But the reason it's blurry is because they put a little prism in the focal plane of the telescope that then dispersed each of the images of the stars into their spectrum. So you can see that as you're on the left side of one of these bands, that's the blue light coming from the star, and as you move to the right of one of these bands, that's the red light of the star. So it's only the spectrum of the optical region or the visible light region of the star's light. Now below in the colored rainbow bar that I show, that is a representation of the color of light as a function of its wavelength. And its wavelength, in this case, is measured in nanometers, the little nm. And you see on the right there in the red, there's a line of missing light. We call it an absorption line. It's the light has been absorbed out of the rainbow or out of the spectrum. This is at 656 nanometers. And you'll notice that in the green-blue, there's one at 486, and then as you go down into the deep blue, 434 and 410. And it turns out that these are due to the way electrons move around in hydrogen atoms. And so this is a fingerprint in the spectrum that comes from hydrogen atoms. And so you can actually determine something about the temperature and density of hydrogen atoms in the spectrum of these stars, so therefore in the stars themselves. Now, if you go back to this blurry image on the left, you might be able to see that in a few of the spectra, you can see these dark lines or these dark bands vertically peppered inside of the spectrum. And in particular, you can see them most strongly in the A spectra, the ones that on the right are labeled A. And then it gets weaker as you move away from A. So Annie Jump Cannon at first tried to make sense of these lines in the spectra, and so she basically did what anybody could do at the time, which was to try and organize them into groups to basically understand them. And she started by saying, okay, when those lines, the absorption lines, are the darkest, and in other words, the language we use is they're the strongest. When the absorption lines are the strongest, we'll call that an A star. And the next strongest we'll call B, the next strongest C, D, E, and so on down to about O when she couldn't see any lines. Now, for a long time, nobody really knew what this meant. And then eventually it was discovered that this sequence was giving you, or the strength of the absorption lines, if you will, was giving you information about the temperature, the surface temperature of the star. So they learned that this letter sequence was actually a temperature sequence. But it turned out that the lines got stronger, well, let me put it this way. The lines are strongest when the temperature of the star is around 10,000 degrees, absolute. And when you went to higher temperatures, the lines would get weaker. And if you went to cooler temperatures, the lines would get weaker. And so it turned out that A stars were stars that were in the sweet spot around 10,000 degrees. O stars, it turned out, were very, very hot. There are other ways to determine the temperature in addition to the strength of the absorption lines. So O stars were the hottest, and then M stars were the coolest. So she basically grouped the stars a little more crudely. She put the A, B's, and C's, she sort of put into A, and then the D, E, F, she put into B, and whatnot. And then she came up with this sequence: O from the hottest, B, A, F, G, K, M to the coolest. And so the strength of these absorption lines is related to this spectral sequence. So basically, for now on, I'm going to be talking about stars in terms of whether they're an O star or a B star or a G star. And so basically, I'm going to be talking about the temperatures of these stars. But it turns out, as we'll see when we look at the Hertzsprung-Russell diagram again, which we talked about in Module 10 when we talked about the evolution of the sun, we'll introduce that again. You'll see that the spectral sequence is related to the temperature, but then we're going to find out it's also related to a lot of the other properties of the stars. And so that these letters tell you much more than just the temperature. They tell you about the size, they tell you about the mass, and they tell you about the lifetime and the fate when it dies. So these letters turned out to be very, very important for understanding stars in astronomy. Now, in terms of spectral sequence, this is table 16.1. Actually, I don't think this table might not be in your book, so I'm not sure that number actually corresponds to your book. But what we have on the left column is the spectral type: O at the top, the hottest, and M at the bottom, the coolest. Then the sun, it turns out, is a G-type star, so we'll talk about that a little bit more. Examples of those stars are given in the second column, and we have some of the stars in Orion's belt, which are very, very hot stars. B, another star in Orion called Rigel. A stars, so Sirius is the brightest star in the sky if you live in the northern hemisphere, and you can see that in the winter. It's very close to Orion. F is this type of star that Polaris is, or the North Star. So if you know where to look for the North Star, you're looking at an F-type star. G, the Sun is a G-type star. Also, our nearest neighbor, Alpha Centauri, is a G star. K, that's an example of that star, is Arcturus. That is a very bright red-orange star that you can see in the summer sky. And then M-type stars, examples are Betelgeuse and Proxima Centauri, which is a companion to Alpha Centauri. And Betelgeuse is, guess what, a star in the constellation of Orion. So these were a lot of examples were in Orion or near Orion. O stars are about 30,000 degrees or higher. This is the third column. And then B stars between 10 and 30, and A stars between sort of 10 and 7.5, etc. F stars around 7,000. G stars, like our sun, are around 6,000 to 5,000. Ks are 5,000 to about 3,500. And M stars are less than about 3,500. And so basically, you've learned now that stars do have a range of temperatures, and that those temperatures range from around 3,000 degrees all the way up to about 30,000 degrees. So not crazy hot and not crazy cold. Okay, so there are some key absorption lines that you see in the spectra. I'm not going to go through those. There's a lot of details. It's a whole lifetime of study. You can get a PhD just learning about the absorption line features in the atmospheres of stars and then studying the stars, okay? Um, so one of the things that is interesting about hot stars is that most of their light is coming out in the ultraviolet in the blue part of the visible spectrum. And so those stars appear actually to be sort of a white bluish color. As you go cooler, the peak intensity gets more red. So by the time you get to an F star or a G star in particular, those a G star like our sun is peak brightness is in the yellow. So that's why the sun sort of has that yellow look to us. When you get to the K and the M stars, though, they're cool enough that they peak in the red light and the infrared light, and so those stars, they're cooler. They actually look redder. That's always interesting, like how we always get red and blue, indicating that red is hot and blue is cold. And I think it comes from our hot water and cold water taps in the historically, but in actuality, in the world, a hot object is actually blue, white, and a cool object, meaning around 3,000 degrees, which is 10 times hotter than room temperature, will glow red. So remember that. The hot stars glow blue, or I should say emit blue, and the cool stars are red. Now, continuing with our classification of stars, what we have here again is the Hertzsprung-Russell diagram, or for short, we call it the HR diagram. And just to review what the HR diagram is we plot two properties of stars that we can measure. The first property we plot is the surface temperature, and that's plotted across the x-axis, but it's backwards. The hot stars are on the left and the cool stars are on the right. And so in this case, we're usually going from small to big. As we go to the right, we're actually backwards. So as you can see, we have O stars will be on the left-hand side of the diagram, and M stars will be on the right-hand side of the diagram. And the O stars will be blue because they're hot, and the M stars will be red because they're cool, relatively speaking. Along the y-axis, we have the luminosity. That's a very large number. For example, the sun's luminosity is about 10 to the 33 ergs per second, how much energy and light comes off the star in every second. But what we do is we normalize all the stars to that number, to the sun's luminosity. And so we say the sun has one unit of luminosity in solar units, or solar luminosities. Now, interestingly, as you look toward the hot stars, yes, you see the blue stars are up there in the upper left corner, which is where the top of the diagram is the most luminous objects. And this is a log plot here, so each tick is 10 times more than the tick below it. So we go 10, 100, that's 10 to the 2, then 10 to the 3 is 1,000, 10 to the 4 is 10,000, 10 to the 5, 100,000, and 10 to the 6 is a million. And so you see here that O stars, the biggest O stars, have luminosities that are, wait for it, 1,000,000 times more than the sun. So if you could imagine Earth being around a star that was 1,000,000 times more luminous than the sun, I think it would be pretty hot, okay? And it would be a lot of ultraviolet light and very blue. Okay, interestingly, when you go to the very coolest stars, the M stars, which are down in the lower right-hand part of the diagram, to the right because that's cool temperature, and to the bottom because that's lower luminosity, we see that those have luminosities that are about maybe a 10,000th of the sun. So 10 to the minus 4 is a 10,000th. And so whereas the star temperatures only go from a range of 3,000 to 30,000, which is not really that large of a range. It's a factor of 10 from 3,000 to 30,000. So O stars are really only 10 times hotter than M stars. But when you talk about how much power output they have, an M star is 1/10,000th of the sun, whereas an O star is a million times that of the sun. Okay. Now, this all has to do with properties called hydrostatic equilibrium, because a star is a ball of gas. It's crushing itself under its own mass. And as you go deeper down, then the pressure gets higher and higher and higher to push back on the mass that's above that layer in the star. And at equilibrium, an equilibrium sets up where the size of the star and the luminosity of the star all come together, and the star then sits there in this equilibrium configuration for a long time. And it turns out that they don't all stay in that equilibrium configuration for the same amount of time. We call that time lifetime. Now, marked in green on this diagram are basically the amounts, the lifetimes of these stars as I've described them. And you can see, for example, that the sun has a lifetime of 10 to the 10 years. And that turns out to be 10 billion years. 10 to the 9 is a billion years. And so let's take a look at this. As we go down to, say, the K star there that we show, it says its lifetime is 10 to the 11 years. Well, that's basically 100 billion years. Now, that is a long time, ladies and gentlemen. The universe itself is only 13 billion years old. So that means that when these stars form, these M stars and K stars, if you had formed one of these stars at the beginning of the universe 13 billion years ago, it'd still be around. It's still going to be around for another 90 billion years. So those stars, once these stars form, they really stick around a long time. I mean, they'll be around after the sun is long gone. Okay, even if they formed very early in the universe. Okay, so then we saw that the sun is about 10 billion years in its lifetime. And as we go to an A star like Sirius, they're in the middle of the diagram, we see that its lifetime is about a billion years, so about 10% of the lifetime of the sun. And then as we move up the diagram to the hotter stars, we get to Achernar, that's a B star. And Achernar has a lifetime about 10 to the 8 years, which is 100 million years. And as we go up to stars as luminous as Spica, or Spica, depending on how you pronounce it, then you see that these stars last about 10 to the 7 years, and that's only a 10 million years. Okay, so 10 million years is a blink of a lifetime. If you think about it, it's a cosmic blink of the eye. For example, the KT event that made the dinosaurs go extinct, that happened 60 million years ago. So that the lifetime of one of these O stars can be as much as only 1/6 of the time since from now back to the time of the KT event, the catastrophic meteorite that struck the Earth. So that's a pretty short lifetime for stars. And in fact, if you go up to those really big 60 times the mass of the sun stars up there at the very upper left of the diagram, they actually can live short lives on the order of, say, a few 100,000 years, which is very fast. I mean, humanity only came into being a few 100,000 years ago. So they basically lived that kind of lifetime. That's very short in the universe. Okay, now that I've shown you all of this information, I got it all summarized in these two little boxes in the upper right. Let's look at the extreme stars, the O stars, the hottest, and the M stars, the coolest. I guess one of the last things I forgot to say was when you look at all of these stars along this line, which we call the main sequence, The M stars have small masses, like somewhere between a tenth to 30% of the sun's, 0.3. But in terms of the sun's mass, we see as you go up to, say, Sirius, it has about 3 times the sun's mass. And Achernar has about 5 times the sun's mass, or 6 times the sun's mass. Spica has about 10 times the sun mass, and the most massive stars are around 60 times the sun's mass. So not only is the spectral sequence O, B, A, F, G, K, M a sequence of temperature, but as you can see, as you go from O stars, you're talking about the hottest stars, you're talking about the most luminous stars, you're talking about the most massive stars, and it turns out, I didn't mention it, you're talking about the largest stars. However, there's one thing that is not the biggest about O stars, and that's their lifetime. It turns out their lifetime is the shortest. Okay, so O stars, hottest, most luminous, most massive, largest, but shortest lived, very short lives. Now, as you go to the other side of the main sequence, to the M stars, what do you find out? Well, we know they're the coolest. It turns out they're the least luminous, they're the least massive, they're the smallest, and again, this is the flip. Instead of having the shortest lifetimes, which you might expect because the M stars have the smallest of everything, no, they have the longest lifetimes, and their lifetimes can be exceedingly long as 100 billion years. So now what I'd like to do is I would like to discuss these different types of stars in view of their relative numbers that we see in the galaxy and therefore in the universe, and also in terms of their whether they're good, have good habitable zones around them or not, I guess is the question that we want, or the issue that we want to bring up with these stars. Okay, so the first thing is we want to know which stars basically are the best for going out and finding habitable planets. Are O stars the best? Are B stars the best? G stars, K stars, or M stars? And so I've limited this slide sort of the G and K stars the best, and then to the maybe are the M stars the best? And I'll give you the reasons for that as we go through this slide. First of all, bullet one, there are lots of stars, okay, 100 billion to 400 billion in the galaxy. Some of them are M stars, some of them are O stars, okay? Now, let's look at the table. Let's look at the second column from the left. It turns out that O stars are very few in number, okay? Of all of the stars out there, they represent about 0.001% of all the stars. So these are very rare stars. B stars are about 10% of all stars. A stars are about 1% of all stars. 1 out of 100 stars is an A star. F stars about 2%, G stars 7, K 15, and M 75. So get a load of this. 75% of the stars in the galaxy and in the universe are M-type stars, and 15% are K, and G stars like our sun only comprise about 7%. Other than that, the number of stars goes down drastically as you go to the higher mass, hotter stars, particularly the O stars. Okay, so chances are, okay, if you want to have as many habitable planets out there as possible, there's just not as many O stars for planetary systems to form around. So you're just, sheer numbers, you're just not going to find as many habitable planets around O stars because there just aren't that many O stars to find them around. Okay. Likewise, there's 3 out of 4 stars out there is an M star. So there's a lot of, if M stars have good habitable zones, then you're going to find a lot of habitable planets out there in the galaxy. So let's think about some other factors about whether they're good for having good habitable zones. Okay. So let's consider, we've learned a little bit about their surface temperature already, from the hot to the cold, and we've learned a little bit about their luminosity. Those were on the HR diagram. We learned a little bit about their mass. Those were also on our HR diagram. And we also learned about their lifetimes, okay? And so these numbers aren't exactly identical to what's on the HR diagram because the representative stars on the HR diagram, um, there's a range of O star lifetimes, there's a range of O star temperatures, blah, blah, blah. So the numbers aren't identical, but you can see that they are definitely in the same ballpark. Now, we did say that O stars live very, very short lifetimes, and the most massive ones can only live a few 100,000 years, and say the shortest, the longest ones live about 10 million years. But it's very short, okay? And as we go down to the cooler stars, let's go down to the G and the K and the M stars. Now we're getting into some serious lifetimes. And as we know, life took 5 billion years to evolve to intelligence life, at least. And it took until the Cambrian explosion, about 3.5 billion years after the Earth formed, in order for there to be a lot of diversity of life. So you need some time. You need several billion years and then some. So if you want life to be stable, then you're going to want to be around a star that's stable. G stars, K stars, and M stars are very stable for a very, very long time. So that's why they are winners in that regard. They're also winners because they're the most abundant stars in the galaxy and therefore also in the universe. Now isn't that handy? Just like life needs carbon and nitrogen and oxygen to live, those happen to be the three most abundant elements in the universe next to hydrogen and helium. Gee, isn't that handy? And okay, life wants to be around for a long time. Well, so isn't it handy that the stars that are the most abundant live the longest lifetimes? So it's sometimes amazing how it seems that the universe is fine-tuned to make all this happen just in the right way for life. Okay, so the other thing we learned with the O stars was that they are very, very luminous. Imagine if we were orbiting an O star, that the luminosity was 1,000,000 times more brighter than what's coming off the sun now. Okay, and it's mostly ultraviolet light. So guess what? Good luck. You're going to get cancer and die. And basically, there's too much ultraviolet intensity. It's just too harsh. Unless you happen to be out at the orbit of Pluto or something like that, you might be able to survive. But again, it's highly ultraviolet balanced light. As you go to the cooler stars, the light gets more toward the middle of the visible spectrum, and with G stars, we saw that they peaked in the yellow. That's a beautiful amount of light energy that doesn't destroy life because it's not too intense, and so that's great. And then the K stars, we said, really shone more in the red. If you orbited a K star, it would be very red, and if you orbited an M star, it would be very dim and very red. Remember, an M star is about 1/10,000th the luminosity of the sun. So, looking at the little notes I put to the right of the diagram, then we would say that F, A, B, and O stars, they're too short-lived for life to really take a foothold. And we might say for the O and the B stars that the light is just too intense, so it gets worse. They're shorter lifetime and they're just UV bright and too intense. G stars and K stars, beautifully situated, beautifully suited for longevity and stability and not having too harsh of an environment. M stars, we've always thought in the past, were probably just not enough energy coming off of them, and the habitable zones would be too small and too close to the star. And so that was always considered to be something where the conventional wisdom was that M stars won't be quite as good as G stars and K stars, and probably G stars are the best, right? Because we're around a G star, so G stars have to be the best because, as Carl Sagan says, we're not special, we're not atypical. So we would expect that G stars are going to be this kind of stars you'll find habitable planets with life on them. So, but modern day, we've started to ask, are M stars the best? Okay, now we learned that as the sun ages, it gets brighter, more luminous. And we also learned that as the star gets more luminous, that its habitable zone moves further and further away. And the fact of the matter is, we thought that that means that K stars would have habitable zones that are in closer to the star than a G star, like our sun, and M stars would have one that's even in closer, and it would be a very narrow little shell around the star. Okay, and so we thought that again, too narrow and so close, the planets would be tidally locked, and maybe a tidally locked planet's not conducive for life to really take a foothold. So we had all these ideas that ruled out M stars, but it turns out we've taken a new look at the problem, and I'm going to find out that you're going to find out that M stars win. So in the last slide, I was talking about the relative sizes of the habitable zones for G stars and K stars and M stars. So the upper right hand diagram, I'm showing the relative sizes of the habitable zones for these three types of stars, where the G star, like the sun, is on the left, K star in the middle, and the M star on the right. And you can see that the amount of volume encompassed in the habitable zone of the sun is much larger than the volume encompassed by the K star or the volume encompassed by the M star's habitable zone. The diagram below is sort of an edge-on version of that, showing an M star, a G star, and an A star, just for comparison. Also, I think showing where the orbits would be for certain habitable planets. For example, around an A star, if you're out at Jupiter's orbit, that's where you would find yourself in the habitable zone. But around the sun, it's the Earth's orbit. Okay, and it turns out that for an M star, Venus and maybe Mercury's getting on the inner lip, if you will, of the habitable zone. Okay, so that really shows you that the volume of habitable zones, or the size, if you will, but mostly it's the volume we care about, is much larger for G stars, getting smaller for K, and it's extremely small for M stars. Now remember, G stars comprise 7% of all stars, K stars 15%, and M stars 3/4. It's 3 out of 4. All right. So what we want to do is we want to know, like how many habitable planets might be out there in the galaxy that are around G stars, or how many might be out there that are around K stars, and how many might be out there that are around M stars. So we need to know something about the distribution of planets around these stars. And then we need to know what are the chances that a planet will end up in the volume encompassed by their habitable zone. Now the thing that's nice is the volume encompassing the habitable zone of a G star is very large. So the chances that you'll find planets in the habitable zone around G star are higher. As you go to the K star, that volume is smaller. So the chances that a planet will find itself in orbit in the habitable zone is smaller. And the same thing with M stars. It's very, very much lower probability that you're going to find a planet in the habitable zone because that volume around the star of the habitable zone is so small. So really, this is kind of a numbers game. You basically want to do this probability calculation. You want to know something about the volume of the habitable zones around a given type of star. You want to know something about what percentage of all stars are of that given type of star. And then you want to know something about what are the chances of finding a planet in the habitable zone, and then estimating the product of all these things to figure out what are the chances of finding a planet, or what are the number of G-type stars in the galaxy that have planets in their habitable zone. And then same question, how many planets or K stars are out there which would have planets in their habitable zones? And you do this number of planet density and then volume of habitable zone times number of stars, and you come up with this number. And it turns out, and here's your magic phrase for the day: M stars win, and M stars win big. Okay, so it turns out I'm going to show you in the subsequent slides some numbers that really show you that M stars, when it comes down to it, the total volume of habitable zones around M stars is much greater than the total volume of habitable zones around K stars and around G stars. And so M stars win, and they win big. One of the studies that has helped us understand that M stars really contribute the most habitable zone volume to the galaxy was conducted by the Planetary Habitability Laboratory, or PHL. And when they did this study, they decided to not include all stars in the galaxy, but just those stars that were not members of clusters. So stars that have just come out of stellar wombs, out of their gas clouds, are still clustered together and they disperse with time. And then also other clusters of stars that just exist because they're gravitationally or even loosely gravitationally bound. And so the idea was to look at the stars that were not members of clusters. And so there might be 400 billion stars or 300 billion stars in the galaxy, but at least half of them or so might be considered to be in clusters. So they separated the stars out that way. Then they decided to look at the solar neighborhood, which is a sphere around the sun about 33 light years. And remember that the galaxy itself is 100,000 light years across. So this is really a local neighborhood in the galaxy. And in that region, the 33 light year sphere around the sun, they counted or estimated the total number of M-type stars and solar-type stars, basically the MK and G stars. And their estimates are there's somewhere between 132 and 160 such stars within a radius of 33 light years. Of those, M stars are 126 to 151 of those stars. So you can see that they totally dominate the numbers. And that means that they're only for K and G type stars, the solar type stars, they're somewhere between 6 and 9, certainly less than 10 of those types of stars. Now, if you extrapolate those numbers to the Milky Way galaxy as a whole, you get somewhere around 40 to 50 billion M-type plus solar-type stars, of which 38 to 46 billion of those are M-type stars, and roughly 2 to 3 billion are solar-type stars. So that's a huge difference. That's a factor of about 20, at least, more M-type stars than there are solar-type stars in the galaxy. And so if you take the volume of a M-type star's habitable zone and you multiply that volume by about 38 to 46 billion, you get a very, very large volume of habitable zone. If you then take the volume of a G-type star, for example's habitable zone, which is considerably larger, but you multiply it by a number like 2 or 3 billion to get the total volume in the galaxy, that's just not enough stars to add up to give you more volume than what is in the M-star habitable zones. And so what we find is that M-star habitable zones really are the predominant volume of habitable zones in the galaxy and therefore in the universe. And one of the things that I have here in the box at the bottom is that, if you think that F sub p in the Drake equation is about 1, roughly, that means there might be somewhere around up to 150 habitable planets within the 33 light year radius. That's assuming that there's about 1 planet in the habitable zone for every M star, so that is an upper limit to the number. But predominantly, we will find habitable planets around M stars. It's just the numbers definitely say that. Now I have a diagram on the right here, cumulative detections per year, and basically since the first detection in 1995, you can see the various numbers of planets as a function of year that we have a cumulative number of planets that we've found around other stars. And as I've been saying, it's presently around 4,000. This diagram basically talks or lists the various methods that we have used to detect extrasolar planets. And I'm not going to go into the details of those methods, excuse me, but I just wanted to let you know that there are different methods, from radio velocity to what's called transiting to microlensing, direct imaging, looking at time variations, and things like this, and astrometry, which is basically high precision measurement of position of stars. And one of the things that people use is that the center of mass in a solar system like our own, is not the sun itself, or not the central star. It actually, the center of mass can be offset from the center of the star. And this means that the center of the star and the planets orbit around the center of mass, which means the star itself is orbiting around the center of mass. Now, mind you, the center of mass may be somewhere still inside the star, but the star itself is still orbiting around that center of mass, which means it has a small, tiny orbit. It might be smaller than its own radius, but it is in an orbit. And believe it or not, we can detect that orbit. So we do that with astrometry and what's called radio velocity, measuring its velocity wobble. Most planets have been detected through transits. So we will show an image of a transiting planet later in the lecture, and give you a clue as to how that detection method works. Microlensing uses Einstein's general relativity equations that model the bending of light and the amplification of that light signal that happens when a star passes behind another solar system. The star itself will cause the background star to brighten, and also the planet itself will cause a small brightening. And so we can detect the little brightening from the planet when we measure the light of stars that pass behind planetary systems. Anyway, my point here is that there are multiple methods. They require immense sensitivity and monitoring and data reduction and analysis. But over the years, we have gotten to the point where we have about 4,000 of these detections, and we discovered that F sub p is basically about 1 in doing these exercises. So what is the distribution of these planets around the other stars? And so this is a nice little diagram which shows the orbital period along the x-axis and the mass of the planet along the y-axis. And the mass of the planet are given in units of the Earth's mass. Now, interestingly, the numbers here are given as powers of 10. And just to remind you that if we look at the mass axis, that lower one, 10 to the minus 1, that means 0.1 or 10%. 10 to the 0 actually is 1, the number 1, and you can see that the Earth is on that line, so that's an Earth mass. 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000. And so on this diagram, you can see that Jupiter and Saturn are somewhere between 100 and 300 times the mass of the Earth. And that, for example, Uranus is just around maybe 15 times, a little over 10 times the mass of the Earth. Now, as time is given along the x-axis, the period, you can see that the Earth there has a period in days of about 325 or so, give or take. And Uranus is up at around about 30,000 days, and Jupiter is up at around 3,000 days. So Jupiter takes about 10 years to go around the sun, and Uranus takes about 100 years. Now, those aren't exact numbers, but they're round numbers. I think Uranus is more like 240 or something. So, what do we see here? First of all, we see that the different types of planet detections pick up different classes of planets. So this is called a selection method, and this is kind of an important thing in science, that the way you actually do your experiment might actually have a propensity to select out certain things more than other things. And so, for example, RV means radial velocity, and that's measuring the back and forth velocity wobble of the star, tends to pick up big planets because big planets tend to make the wobble of the star easiest and biggest to detect. And so you can see that most of those are these Jupiter planets that have periods on the order of, say, 100 days, about the length of the Earth's um, year, basically, or period of orbit around its central star. But what I want you to walk away with here is that so far, even accounting for our selection methods, that some pick up different planets, the transit method has definitely shown us that most of the planets are in close to their stars that we've been able to detect with the transit method, and that they are pretty much what we call super Earths. They have masses that range between the Earth's and Uranus's, and most of them are sort of in the order of about 8, 9 Earth masses, and we call these super Earths because they're probably rocky-ish planets that are bigger than the Earth, but they're in close. Now, I want you to understand here that most of these planets orbit their star within somewhere between 10 and 100 days. So some of these take less than a month to go around their central star, and some of them take, say, about 3 months to go around their central star. Now, that's pretty amazing when you think about it, that these planets are really zipping around their stars. And so we want to ask the question, are they in habitable zones or not? Well, we'll get to that in a bit, but I just wanted to show you this distribution of known planets in terms of how long they take to go around their central star, and what their distribution of masses are. And so what we see here is that super Earths, close-in super Earths, and sort of sub-Neptune planets are the most common. Here's another similar diagram in which a colleague of mine has marked the planets by sort of our general categorizations. We have hot Jupiters, cold Jupiters, young Jupiters, and warm Neptunes and super Earths, effectively. And you can see on this diagram that it's not plotting along the x-axis, it's not plotting orbital period, but actual separation from the central star this time, which I think is a little bit more physical and easy to understand. Again, you can see that 1 astronomical unit is where the Earth is, and right there under the super Earth statement, you can see the Earth and and Venus down there as little pictures. And let's see, then along the y-axis, again, we have the planetary mass. And again, they this time are not plotted, interestingly, in terms of Earth masses, but it's plotted in terms of Jupiter masses. So Jupiter now on this scale has a mass of 1, and you can see that Earth is down around less than 100th, 0.01, and or less than 0.01, which is 100th of Jupiter's mass. It's about 1/300th of Jupiter's mass, actually. So you can still see that the masses scale the same way. It's just that the 1 has been shifted, and we see that these warm Neptunes and super Earths, like I said, are in close to their stars. They can orbit between 10 days and 90 days or so. And they're about 1/10 of an astronomical unit. Some of them almost 0.01 astronomical units. Now, I want you to look at the bottom of the diagram there where Mercury is. So Mercury on this diagram is at around zero point 0.4 astronomical units, and you can see that that would be very hot around a G star, as you know, but most of these super Earths are in much closer than Mercury is to its own star. The difference is that a lot of these super Earths are around much cooler M stars, and so some of them actually could be in the habitable zone. In fact, I'll show you an example of that at some point in time coming up. Anyhow, hot Jupiters are massive planets like Jupiter, which are very close into their central star, about 10% of the Earth's distance out. So this was something we never expected to find, but our experiments demonstrated that the galaxy is filled with stars which have hot Jupiters orbiting them. And then you have cold Jupiters, like our own Jupiter, which are further out and therefore are much cooler. And then you have this weird body called young Jupiters. These are in stars that are still forming their planetary disks. So anyway, this is an interesting diagram showing you the distributions of planets. Now, as far as the color coding has to do with how out of round the orbits are. So as you know, the Earth is in a almost perfectly circular orbit. It's only 0.03 out of being a circle, or 3% out of being a circle. And so this heat bar, if you will, on the right-hand side, going from blue at 0 up to about almost 1 in the red, as you go from blue to red, you're looking at planets that are in more elliptical orbits or more out of round orbits. So blue points, they have circular orbits, what they call an eccentricity of 0. Green points are way more out of round. They have much more elliptical orbits. And then yellow and orange points are highly elliptical, almost like a comet's orbit, where they come in close to their star and then they move way, way far away. And the interesting thing is what's being plotted here is their average distance from the sun, sometimes called the semi-major axis of the ellipse. So that's just to give you an idea that you can see that most planets have been circularized in the sense that they still orbit in ellipses according to Kepler's first law, but like the Earth, those ellipses are quite close to circular. Of course, since we're studying life in the universe, we're very interested in knowing whether we can find Earth-like planets. So scientists have come up with a way of trying to compare planets to the Earth in terms of habitability, and they use this indicator called the Earth Similarity Index, or ESI. And this is an index number which ranges from 0 to 1. Of course, Earth is the Earth, and it defines what 1 is on the ESI scale. And then 0 would be absolutely and totally un-Earth-like. Okay, so on this scale, you can see where the various planets in the solar system fall. So you have Mars around 0.7, Mercury around 0.6, and Venus a little under 0.5. And then, of course, the gas giants somewhere below 0.3 to 0.2. Now, the way this is designated is that any planet that has an ESI that's somewhere between 0.8 and 1 would be considered to be Earth-like and therefore possibly habitable. Okay, so the ESI looks at several properties of the planet, and the very bottom paragraph gives that list. Its radius, the average density of the planet, the escape velocity of the planet, and the escape velocity actually is a combination of the planet's mass and its radius. So if you know the mass of the planet and you know the radius of the planet, there's a simple formula: g times the mass divided by the radius squared. Take the square root of that, and you get the escape velocity of the planet. So it's a very simple combination of those properties. And then the surface temperature of the planet. So that would be an absolute temperature, and the Earth's average absolute temperature is somewhere around the high twos, 290, 295, or something like that, just under 300. So if you can measure these properties of a planet, then you can actually plug them into a formula, and you can come out with an Earth Similarity Index. So I have to tell you, of course, that the Earth Similarity Index is something that people try to measure for many of the exoplanets that have been discovered. So this is a nice diagram showing you a small sample of the top ESI planets, if you will, those that range between zero point 0.8 and 1. These are the top candidates that we know about. And again, this is to remind you that, somewhere around 30 years ago and 25, 30 years ago, we actually had no idea about any of this stuff. And then on the left-hand side of the diagram, you can see that we're talking about the habitable zone. We have the region that's just right, too hot, too cold. So the Earth Similarity Index does not account for where the planet is in whether it's inside, within, or outside the habitable zone. It just looks at these four properties, which again are given across the bottom: the radius, the density, the escape velocity, and the temperature of the planet. Now, in the two little circles, you see two telescopes, the European Southern Observatory and the Kepler Space Telescope. And that's just to show you that these are two of the main telescopes that were involved in doing these studies. And Kepler is a space telescope, as it says, and its mission is basically over, but it's responsible for the lion's share of all planets that have been detected. It was a planet detecting machine for years, and it used the method called the transit method. And in the next slide, I will show you a diagram of how that works. So to the right here are the leaders. They are given names such as Kepler 438b. Basically, in the field, there are stars, they are numbered, and then so the Kepler spacecraft did not just scan the whole sky and look in random directions at random stars. It actually pointed at one patch of sky, which is microscopic to the visible eye. It's just a tiny little patch. It's over by the Big Dipper to the north. And in this region, all these stars were numbered, and then they were all observed by taking images of this part of the sky and looking for the brightening or the dimming of the star, which would happen if a planet passed in front of the star, and that's why we call it the transit method. So Kepler 438, the star itself is A, and then the planets are B, C, D, E, and so on down the alphabet. And you can see that Kepler 438b is the biggest winner. It's got an Earth Similarity Index of 0.88. And then there are some stars that were not observed by Kepler. Here's one called Gliese 667c, 0c. And this one was observed by the European Southern Observatory's telescope, and it has a Earth Similarity Index of 0.84. So on and so forth. We really don't know what the colors of these planets look like. These are artists' conception of them, but the point is we are starting to locate Earth-similar planets, and now the next thing to do is to study these planets in detail. And so that's what we're going to talk about in the next slide, is how do you go beyond something like a single number like the ESI to actually measuring what the heck is truly going on these planets and seeing if in fact they are habitable in terms of our three criteria: energy, chemical elements, and liquid water. So finding habitable exoplanets, I'm not gonna lie, is really tough business, particularly at this stage. Now we're gonna have some future missions that we talked about in the Drake equation, that what those future missions were that are going to go after this. And so in the next 10, 15 years, I think we'll have very good measurements of the properties of those planets with their that have the high Earth Similarity Index. So this is a diagram in the lower right which shows a planet passing in front of a star, and you have what's called a primary eclipse where the planet passes in front of the star, and then you have a secondary eclipse where the planet passes behind the star. Now, this is the method that Kepler used to find planets. So it only could find these sort of edge-on planetary systems out there. If the planetary system was on its side, then the planets would be going around, and we wouldn't see them pass in front. But if the plane of all the planets is on edge relative to our viewing angle, then we would catch all of those. So here's an example of a planet passing in front of its central star. And when it does so, it blocks out some of the starlight. You can see that by they blackened where the solid planet itself is. That starlight is blocked. And so the total amount of light we would detect from that star is dimmed. And we can detect that dimming. And we can see that as the planet goes around, it dims it. And then it comes back around, it dims it again. It comes back around, it dims it again. So we can actually measure the light period of the period in time of that light dimming, the frequency at which it happens, and that can tell us about the planet's orbital period. And then we can learn about the size of the planet by looking at how long the transit lasts, and how much the light dims. So if the light dims more, it's a bigger planet. If its light dims less, it's a smaller planet. So we can estimate the size of the planet. It's pretty amazing what you can do with light. Okay, so you'll notice also in this diagram that the atmosphere of the planet is kind of shown as the blue ring around the planet. Okay, assuming the planet has an atmosphere. And this is not blackened out because some light will actually pass through the atmosphere. And that, ladies and gentlemen, that little bit of light that passes through the atmosphere is the light we are going to try and tickle out of the entire light beam of that star. So think about it. We have the whole, the light coming that we're capturing is mostly from the star, and then it gets dimmed a little bit from the planet, and then lurking in that light is a little signal, completely swamped out, of absorption lines that come in from the atmosphere. And our job then is to tickle out those absorption lines and then understand the absorption lines give us the chemical composition and temperature of the atmosphere and things like that. So that's what we're after. Can we detect water vapor? Can we detect methane, ozone, carbon dioxide? What's in the atmosphere? Okay, so basically, as written in green here, we measure the star spectrum when the planet's behind the star, and then measure the spectrum when it's in front of the star. We difference the two of those spectra, and when we do, we subtract out most of the starlight or all of the starlight, and we're left with the residual spectrum of the atmosphere. So we have to subtract these spectra, and then we can study that residual or subtracted out spectrum. So before we go into talking about what the modern astronomers do to try and measure these chemical compositions, I want to remind you of the exercise we did where we looked at Mars, and we looked at Venus, and we looked at Earth, and the Galileo spacecraft had measured their properties. And so those were very crude spectra, if you remember when we discussed that. What I'm showing here are actual models of the different atmosphere spectra. Okay, so what are we looking at again? We're looking at the spectrum of Earth. That's the sort of blue-purple line. We're looking at the spectrum of Venus, and that is the yellowish line. And we're looking at the spectrum of Mars, which is the red line. And along the bottom, we're looking at the wavelength. Again, this is in the infrared. There's micrometers or microns. And so a micron is a millionth of a meter. This is just beyond the red band of the visible light into the infrared. And so we can see, if you might recall, at 15 microns, we have the carbon dioxide features that we see in the planetary atmospheres. And then if you go look at the Earth's spectrum around 10 microns, you see the O3, written in green. That's the little absorption line that comes from the ozone in the upper layer of the Earth's atmosphere. We have this very large dip here in the middle at about 2 to 3 to 4 microns, that large band of light that's removed, and that's due to water vapor in the Earth's atmosphere, but it's due to carbon dioxide molecules in the atmosphere of Venus. So you can see that even in the same wavelength region, you can have light being removed, and it's hard to tell the difference if you don't know what you're looking at. You have to be an expert, know what you're looking at to determine whether these features are due to water or due to carbon dioxide. And you can see that the shape of the spectra are different down there in the valley of that absorption, and that provides some strong clues. You can see that Mars has also carbon dioxide, very strong, and but not necessarily any sign of water vapor either. So this is, if you remember right, we were able to detect these differences very crudely with the Galileo spacecraft in the 90s. These are computerized models of the atmosphere, what the spectra look like, and I'm showing them because that's really an important part of how we actually can determine what type of molecules are in the atmospheres of exoplanets. We have to measure some data of the spectra, but then we have to actually understand all the undulations and shape in these spectra. And so we do that by making models of the spectra. And so what you'll do is you'll put a little more carbon dioxide in the atmosphere of your model, and you see how it changes the spectrum, and then you overplot your spectrum on your data and you see whether it matches better. Effectively, that's what people are doing. But the modeling is a very important aspect of getting or extracting information from the spectra or the data themselves. So the modern view is a little bit more sophisticated. On the left-hand diagram, I'm basically trying to show you a schematic of how the starlight passing through the atmosphere can be modified. So in the top panel, you can see the planet, and then the little blue dots are representing molecules in the atmosphere. The star is way off to the left, out in space to the left, and the Earth, or our solar system, is way out to the right, miles to the right, and the other star is, definitely, maybe a mile to the left, and the Earth, of course, would actually be as far away as Pluto or something like that on this diagram. So what I'm trying to say basically is this is a close-up side view of the light as it comes from the star, the central star the planet orbits around on the left, and passes through the atmosphere and makes its journey through space and the galaxy to eventually be observed in a spectrum that human beings have collected in a telescope. So as that light passes through, the little blue and yellow and orange lines there are trying to show you that some of the light is being knocked out of the light path on its way to Earth, therefore being absorbed, and therefore we can detect it being missing from the light that actually makes its way and journeys to Earth. Now, if the starlight misses the atmosphere, then none of the light is removed from the light path, and so we get this pure stellar spectrum, okay? And that's the part that we have to subtract out of the starlight that went through the atmosphere to get that residual spectrum to measure the properties of the atmosphere. Now, it turns out that if there are clouds, you can actually have the starlight be blocked a little bit, more so than just scattered. And so we can actually learn a lot about the cloud thickness and cloud cover, as well as the chemical composition of these planets. So, what are the kinds of things that people put in their models? They put in basically the scattering properties of the light. That's what we're calling the blue of the sky. They'll put ozone in, they'll put oxygen in, they'll look to see if there's any features that have to do with vegetation, with water vapor, with carbon dioxide and methane, and of course, lots of other molecules like titanium, sodium, oxides, nitrous oxides, and things like that. So, on the right hand side, there is a planet, a spectrum of an Earth like planet, which is showing all the various different features. There's the methane that you can see there on the right in the infrared, carbon dioxide features that you can see in the infrared. And as we move into the close to the optical, sort of in the center there, we can see the water vapor bands. Those are highly suggestive of habitability. And then if you look in the optical, and I'll honestly tell you that we haven't really, don't have the detailed data to go here yet, but this will be the future. We can look for vegetation bumps indicating absorption due to the presence of plant life. That would really be what we call a bioindicator. And then you can actually see the scattering of blue light out of the atmosphere that's being shown around the blue light period of the optical in the upper left corner. That long dip would indicate that blue light's being scattered. Now, that's how come our sky looks blue, is because it is very efficient at scattering blue light. And so whatever direction you look, you see blue light because it's being scattered everywhere from all directions. And that would be, that kind of dip in a spectrum would be indicative of a blue sky. So that would be very interesting as well. Okay, here we are at our second to last slide. And this is a diagram of some data from an exoplanet, and those and some models of exoplanets. And so basically along the bottom you have the wavelength, again in micrometers. This is actually mostly in the visible light area. So 0.8, 0.6, that's very, very red light. Okay, 0.4 is getting into the blue light. So then we have the transit depth, or basically how much light has been absorbed. Okay, so the data themselves are given by these little dots that have the bars on them, and the bars represent our uncertainty in the data. So our best measurement is where the dot is, and then we don't know whether the dot really should be placed up or down somewhere along those bars. So that shows you something about the uncertainty in the measurements. And so there's some blue data, there's some red data, which are called RI, and then there's some infrared data, which are called Z. And you might see that in the legend at the top. The blue points are called 600B, the green 600RI, and the red ones 600Z. And that's just to say that they're in different wavelength bands using different instruments. Okay. Now, this is pretty complicated, but I'm going to try to distill it down for you pretty well. They have a best fit model where they've modeled the atmosphere in the ways that I've talked about. And their best fit model is given by these little yellow diamonds that you can see are overplotted along a black line there as well. So basically, if they put in some water vapor and TiO molecules and some sodium, then they play with the relative amounts, then they get different models. And the best fit model there is given by the gold diamonds. Now let's say, for example, they take all the titanium oxide, the TiO, and all the water vapor out of their atmosphere in their model, and they model it. They get the black line. Okay, so if you go to the lower right, you can see that black line is goes completely under the data out there at 1 micron, under the Z band, under the red data. And so you can see that a lot of the undulation of the data has to be coming from some titanium oxide and or water vapor. And so it's really nice that their smooth model definitely shows that there has to be some of those chemical elements in the planet. And in fact, when they put no water vapor in, you can see that they get pretty much the same result. That's the orange line. It follows along there. So it turns out that there must be some water vapor in this planet. And so that is a spectacular result if you think about it, even with the noisy data that you have. So I'm not going to go much further into this speculum, and just to show you that's sort of the details of how they look at this. They do a mathematical best fitting to the data, so that it's all done in a quantitative way. It's not, oh, gee whiz, the line goes through the data, or gee whiz, the line doesn't go through the data. It's very quantitative. Interestingly, I just want to say that if you look at the blue data, you can see that this planet has a very hazy atmosphere. They have to model haze in it in order to get this dip here that's sort of around 0.4 to 0.6 microns in the blue. So that's another thing to indicate to you that we can learn a lot about these planets. And unfortunately, I'm sad to report that many of these planets have very foggy and smoggy atmospheres. We've kind of been disappointed that some of these planets actually have pretty smoggy atmospheres as far as the chemical constituents of their atmospheres. Welcome to the last slide of this lecture. And what we want to do now is step a little bit beyond the planets and looking at detail at planetary atmospheres, Earth Similarity Indices. And what we want to do is sort of get a meta view of the galaxy and ask ourselves, where in the galaxy might there be a sweet spot for finding these habitable planets? And the bottom line is, if you think about the Drake equation, which was studied in the last module, the Drake equation just talked about the rate at which new stars form and what fraction of those have planets, etc. And it didn't really think about limiting what region of the galaxy might be the best. And my point is that the Drake equation over the years has come over quite a bit of criticism for not really accounting for all of the various factors that we should be accounting for. It still serves as an excellent skeleton around which to rally our thoughts to try and understand how many technological communicative civilizations there are in our galaxy. But on the other hand, people have written a lot of scientific papers since then over the years trying to add terms to it or make corrections to it or things like this. And in fact, you'll notice in the Drake module, the last file that I attached turns out to be a paper that was written only this year, which is a reformulation of the Drake equation, yet again, that accounts for a great deal more that we know now than Frank Drake did back in the early 1960s. Now, everything I'm going to say to you on this slide, Drake didn't know. That our understanding of our own galaxy was super crude at that point in time. We really didn't understand its overall structure and dynamics, or the distribution of how certain stars have a propensity to live in certain areas of the galaxy, for example, or whether the density of stars was higher in one place than it is in the other. Okay, we know all that stuff now. We understand the cycles and life cycles of stars so much better, and we know something about the migration of stars around the galaxy, which is also something new that's only less than 10 years of understanding, that stars actually do a lot of migrating. They might be born at one location of the galaxy and then spend most of their life in another location after they migrate. Anyhow, you can see in this diagram that there seems to be a sort of meta-galactic habitable zone that is not in the center of the galaxy and is not out in the edge of the galaxy. It's somewhere in this sort of, you know, 50% on the way out to about 90% of the way out from the center of the galaxy. And so, what are the arguments for this? Well, along the right-hand side here, I've broken it into the inner region, which has a bar, which Drake didn't know about, to the intermediate region, which is where the sun lives, and then the outer region. And so basically, the density of stars is very high in the center, in the very center, which we call the bulge. And when there's a lot of stars close together, and some of them are exploding as supernovae, they're going to disrupt their neighborhoods quite a bit. And so it's believed that this is an area where there's too much disruption going on, too much chaos, and not to mention we've got a black hole down there. Of course, that only affects the very, 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 very center, but there's a lot of high energy light that bathes that region of the galaxy due to the black hole. And in the center of the galaxy, crossing this bulge, is a bar. And this is a place where stars are migrating in and out, sort of inward toward the center and then shooting through the center and coming out the other end. And it's also a very chaotic place where gravitational influence is probably disrupting the planets to remain stable in orbits and things of this nature. So this is considered to be kind of a chaotic zone, the inner region of the galaxy, where we don't think that this is the sweet spot of the galaxy for finding habitable planets. Now, the intermediate zone is quite good. First of all, the density of stars is not too high, and it turns out that you have a sort of moderate rate of supernovae going off. And, you know, supernovae are the exploding stars, and when stars explode, they by that time they have fused and formed the chemical elements of the periodic table in their cores, and when they explode, they spread that gas back out into their local area of the galaxy. And so this is a way of seeding future planetary systems with the chemical elements required for life. And our sun is a second or third generation star, which had been seeded previously in this region of the galaxy by a supernova or multiple supernovae. So again, remind you that your carbon, nitrogen, oxygen in your body and that you're breathing all were in the core of a previous generation of stars in our location of the galaxy. Now, this means that you have basically the right area. You have enough supernovae that you can distribute metals, or I should say the chemical elements for life, through the galaxy, and you have high enough rates of new stars forming and things like this that is basically the sweet spot. The outer region, the star density is getting a little lower, and so there's just not as many supernovae out there. Now, we know that these chemical elements do get distributed around the galaxy through other processes, but in terms of what we would call in situ seeding of these chemical elements, in situ means from within, there aren't really as many supernovae out there because the stellar density is lower, and therefore you're not putting as many metals and chemical elements for life out there. So you're not going to have as many stars, number one, and number two, they're not going to have as high of metallicity. And I keep calling it metallicity. That's the astronomer's name for every element on the periodic table besides hydrogen and helium. So the chemical elements for life, basically. Now, if you flip the galaxy on its side so you can see it edge on, I've got sort of a schematic diagram here in the lower right. And so you have various populations of stars, from older stars to the most extreme young stars. And this diagram is a little bit tricky to read. It's using these things called stellar populations, halo population 2, blah, blah, blah. Don't worry about those. But what I want you to see is the blue thin line in the center there, called the extreme population 1. This is sort of the type of star that our sun is. These are the types of stars that are the newest generation of stars in the galaxy. Let's put it that way. And these are the stars that have the highest metallicity content, or chemical composition polluted with more of the periodic table of elements from stars. And so this thin disk is believed to also be the very, very sweetest spot for finding habitable planets in the galaxy. So basically, in this intermediate zone, this green ring that you see when you're looking down on the galaxy, and then if you turn the galaxy on your side, a very, very thin layer in that area. And that would be considered to be the sweet spot or the habitable zone of the galaxy, if you will. And of course, that was not part of the Drake equation, but something we'd like to end the course with. So, thank you very much for attending the course. Thank you for enduring just staring at slides and listening to my voice. I apologize. I'm not a dynamic speaker to a computer, so I hope they've been interestingly enough for you to get through them. Thank you for sticking it out during this difficult and uncertain time, doing the homeworks, the quizzes, and things like that, watching the lectures. I will be shortly this week announcing the final exam. You'll see a message come through on that. And if you want to contact me for any reason, again, I will be on Zoom Tuesday and Thursday from noon to 1. If you don't know the Zoom address, ID, or the room number, let me know. I will send it to you, but it should be on your Canvas. And I just want to remind you to take the attendance quiz for this lecture, and everything will be due by Friday at midnight at the end of this week. And other than that, thank you very much for your attendance, and I hope I'll hear something from you or see all of your work come through by the end of the semester, and that I hope you have a good summer. I hope you'll stay smart, listen to the scientists, and in the end, I just want to say, if you haven't gotten bored and stopped listening by now, I hope that you've learned a lot about life in the universe in this class. I hope that you will pay attention to the news as it comes through, as we learn and discover about Earth-like planets and habitability, and learn about that term N sub E in the Drake equation. And gosh, I hope some of you actually get interested enough that you might want to become scientists. We could use more good minds, and we could use more people listening to the scientists who really do know what they're talking about. And I wish more politicians would do so. And this period of time has been a strong indicator of that. Anyhow, pay attention, keep your eyes open, enjoy the journey of humanity, be a good human, and good luck with your college career, and take care.